about, yesterday we talked about Schwarzschild metric. Oh, I guess I should start recording. It is being recorded. Okay. So yesterday we derived a Schwarzschild metric, and so now we want to continue discussing features of this Schwarzschild metric. Now, one thing that we should naturally do is that we found this metric, we should study what are the orbits of this metric, how particles move in this metric. And we know that in general relativity, the free particles move on geodesics. So we would like to solve the geodesic equations in this background metric. It's perhaps finding the most general solution is not easy, but under some assumptions, like for instance, looking for circular orbits or this sort of things, those can be those kind of orbits can be found relatively easy. And in the notes, I have included one particular example of a circular orbit, the innermost circular orbit that one can have in Schwarzschild geometry. So as we reviewed yesterday, if we go far away from R equals RG, then the Schwarzschild geometry is the same, will be the same as what we expect from the Newtonian gravity, and therefore the orbits would also be the same. But when we go closer to RG, the gravitational radius, assuming that there is no matter, then the things will start changing, and we will have different behaviors. Okay, so let me start writing something. So what is the topic of today? First of all, we Schwarzschild, which are basically the geodesics, and geodesics are the solutions of the following equation, right? So I assume you are familiar with the geodesic equation. Is that right? Yes, yes, no. Have you seen the geodesic equation? Okay, so the geodesic equation is d by d tau of g mu nu dx nu d tau equals 1/2 d mu g alpha beta dx alpha d tau dx beta d tau, where tau is so if we are talking about time-like geodesics, then so for time-like geodesics, tau is the proper time, which is the same as the line element, or then the square of the line element. So d tau squared will be equal to minus ds squared. in my conventions, because I'm using mostly plus convention. So a time-like particle will have negative ds square, but it will have positive d tau square. And if you have a null geodesy, then normally I would replace tau with another parameter sigma, which is called the affine parameter. Because for null geodesics, the proper time is 0. So we have to choose a different parameterization for the curve. And there are good choices of parameterizations. There is no unique choice, because we can always rescale sigma and nothing changes. We'll get the same equation. We can rescale by constant and nothing changes. Okay, so this is the geodesic equation. This is a very important equation. So let me pause it. Okay, now we ask how to solve these equations on Schwarzschild geometry. We can consider various orbits or various trajectories. One example which is useful and nice is explicitly solved in the notes, and then you will have several other examples in the exercises in the homework problem. So I won't go through that example, but what we really want to do in this lecture is to understand the situation with R equals RG in Schwarzschild geometry. Because so if we so actually I go to a new page, and we want to, the main topic of this lecture is the extension. Extension of Schwarzschild geometry. Or in other words, we want to discuss Kruskal coordinates. And if we have time, we also want to talk about the conformal compactification or conformal diagram. So let us again rewrite the metric. So as we noticed yesterday, when R goes to RG, so as R goes to RG, the metric becomes singular. Now this singularity, I claimed yesterday that this is a coordinate singularity, so we can go beyond that. Now let us first do an exercise using the geodesic equation to at least get some idea about the nature of this singularity. So the exercise is to, let us ask the following question. Imagine there is a, so here's the exercise. I want to ask you to think about it a little bit. So exercise is that consider a particle that is dropped into this dropped at zero velocity at r equals 2rg. So we have a particle freely falling from r equals 2rg to r equals rg. The question is that how long does it take? How long does it take in proper time, tau, and how long does it take in the coordinate time, t? Assuming that it starts from rest at rg. So falling from rest at r equals 2rg. So this is just a radial motion. It is at rest at r equals 2rg, then it starts falling, and we want to calculate the time it takes to arrive at r equals rg. Is this clear? Is there any question about the question? Okay.